Okay, we're ready to start the next section, section 7.2, trigonometric integrals. Before we get started, let's look at the next two slides. These are formulas I will give you. This will be attached to every test from test 2 forward. It says if I want to integrate the tangent of x, it's equal to the natural log of secant x. These are things you do not need to memorize. There are things that I will need on the test. Some of this we haven't even covered yet. So, like this stuff here, we're going to cover in the next section. And we will use this as part of the things that we need for the next section. Today we will cover this, I believe. So there's a lot of things that we need to cover, and there's a lot of things I don't think you really need to necessarily memorize. You'll learn them over time. The problem with this stuff here is I'm giving it to you, so when you have that on the test, if you can't get them correct, I will be a little harsher. So what I had to do is flip it over onto the last page of the test. A lot of students will tear that part of the test off, so they have it. Anyway, so let's get started. Given a problem like this, I don't know how to solve it. I have a sine squared times a cosine of x. Well, here's something we could do. This whole section is all about u-substitutions and picking the correct u. I could say, well, how if I let u equal sine of x? Then du is equal to cosine of x dx. Well, that's good because cosine of x dx, here's my du, right? This is my u. So now I have the integration of u squared du. I can integrate that easily. That's u cubed over 3 plus a c. And we know what u is. U is just sine of x. So I have sine cubed of x all over 3 plus a constant. So that's all we're doing. We're going to look at these problems and see what trick can I use to manipulate this problem. So this is a very simple section. It's, again, this chapter has a lot of bookkeeping, as I like to say, because there's a lot of things I just have to keep track of. And here, again, what am I going to pick to be u? I'm going to do the same u. I'm going to let u equal the sine of x. That means du has to equal cosine of x dx. So now I have a 2 plus u cubed plus 3u squared du. That's an easy integration. 2u plus u to the 4th over 4 plus u cubed. Right? And then I'm going to substitute back, and I want about plus c. So 2 sine x plus sine to the 4th x over 4 plus sine cubed x plus a constant. Again, it's an indefinite integral. Let's look at the next slide. Well, I'm not going to pick u to be sine x in this problem because it doesn't make sense. Because my du would have to be under the square root, and I don't want that. We wouldn't want du to be in the denominator. We want du to be where it is, right? Because we have this dx that we have to worry about. So this time I'm going to say let u equal cosine of x. So du is equal to minus sine x dx, or minus du is equal to sine x dx. Now I have a substitution I could work with. Instead of writing the square root of u, I'm just going to write the u to the 1/2 du. I can integrate that easily. That's 3/2. I need a 2/3 here, plus a c. I don't want to forget my negative that was on the outside of that integration, right? Because I had this here. I need to have that negative there. So I don't want u. I want to have it in terms of the original thing. So I have cosine 3/2 x plus a constant. So as you can see, these aren't hard. This is pretty easy stuff here. So here's what we're doing. We're saying, giving an integration in terms of sine x and a cosine x, where I want to have it in terms of a cosine x and a single sine x. Some things I should keep in mind that I know that cosine squared x plus sine squared x is equal to 1, and I can manipulate those. So I can get sine squared x to be something else. And I can get rid of sine squareds or cosine squareds because of double angles. So cosine cubed x. Well, I don't I don't know how to integrate cosine x. I can't say let u equal cosine x, du is equal to sine or minus sine x dx, because I don't have the sine. So I'm going to have to manipulate this. So this isn't a good plan right now. So I don't want to plan out what I'm going to make u and v or u and du. So let's rewrite this. Cosine squared x times cosine x. I'm breaking it apart. And I now know that, look, cosine squared x is equal to 1 minus sine squared x. So I go here, 1 minus sine squared x, cosine x dx. So I now have something I can use the u substitution. Let u equal the sine of x. And du has to equal the cosine of x dx by substituting 1 minus u squared du. Now that I have that, I can then integrate. And I get u minus u cubed over 3 plus a constant. But we want to get everything back in terms of x. So I have a sine x minus sine x cubed over 3 plus c. And again, I don't want to forget the c because it is an indefinite integral. So now here we go. I have a bunch of sines and cosines, but you notice sine is an odd degree. So I can siphon off the even degrees. So let's rewrite this. I'm going to rewrite sine as sine squared x squared, because that would give me the sine to the fourth of x. I still have a sine x. Now I have 5 degrees of sine cosine squared x dx. And then, as we saw before, sine squared, I can rewrite that. So I have 1 minus cosine squared of x squared. I'm going to rewrite this in a different order so that I can pay attention that here's my parts here. I could say let u equal cosine x, right? Du is equal to minus sine x dx. I don't have that minus, so I'm going to add that. I'm going to multiply both sides by the negative 1. And there's my oops, wrong color. There's my substitution. So now I have 1 minus u squared u squared du. Now I'm going to expand it. I get 1 minus 2u squared plus u to the fourth times the u squared du. Then I'm going to distribute that u squared minus 2u to the fourth plus u to the sixth du. Now I can integrate. Now that I've done that, I can integrate. U cubed over 3 minus u to the fifth over 2u to the fifth over 5 plus u to the seventh over 7 plus c, right? Now I have to put back what u was. I want everything back in terms of x, so u was cosine of x. That was cosine cubed of x over 3 minus 2 cosine to the fifth of x over 5 plus cosine to the seventh of x all over 7 plus my constant. Alrighty. So now let's look at this. I'm going to say, look, if I have the integration of sine to the n x times cosine to the mx dx, I'm going to siphon off the odd power, which is what we just did in the last problem, right? When we go back over here, we had sine to the fifth. So I siphoned off the odd power so I can rewrite that, and I got everything as in terms of sines and a single cosine, or everything in terms of cosines and a single sine. That way I can do a u-substitution. It says what happens if both powers are even? Well, based off of what we know about double angles, I know that sine squared x would then have to be, after I manipulate it, 1 minus cosine 2x divided by 2, or cosine squared x divided by 2. This I do not need to memorize. Sorry. This I do not need to memorize. It will be provided on that formula sheet. So if we go back to the formula sheet, here it is. See, there's the one, and there's the other. So I will be providing that for you. It was just written in a different form, but it's the same thing. So, sine squared 2x. I mean, sine squared x, sorry, I'm looking up top. I can rewrite this. I can rewrite this as, instead of sine squared, put a 1/2, 1 minus cosine 2x dx. Why do I want to do that? Because it allows me then to integrate, because I can integrate this easily. 1/2. The integration of 1 is x. The integration of minus cosine x is a minus 1/2 sine 2x plus a c. So I have a 1/2 x minus a quarter sine 2x plus c. So these are, again, not a bad problem to work with. I just have to figure out how to handle this, what I'm going to go and manipulate. Sine to the 4th x. Well, I can rewrite that again using the rules I have as sine squared x being squared dx. And some people will just write this instead because it's easier for them. Sine squared x times sine squared x dx. It doesn't matter. You're going to get the same answer. So now I'm going to say, well, sine squared x is the same thing as I write 1/2 times 1 minus cosine 2x squared dx. So this 1/2 here is being squared, and I could square it and bring it on the outside, giving me 1/4. That gives me 1 minus cosine 2x, and that's getting squared dx. Well, I'm going to have to square that and expand it. So when I square that, I get 1 minus 2 cosine 2x. Squaring the cosine 2x, I get plus cosine squared 2x dx. I need to figure out how to handle this part. Well, we know that cosine squared of alpha is equal to 1/2 times 1 minus, plus cosine 2 alpha. So I have the 1/4, 1 minus 2 cosine 2x. I already know how to handle that part. Now I have the new part. Plus, I have a 1/2 times 1 plus cosine. My alpha here is 2x, so I need 2 times my alpha, 4x dx. Well, I'm going to clean that up and then combine terms. 1 minus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x dx. 1.5, I can add those together, right? I can add this and this together. Get 3 halves minus 2 cosine 2x plus a half cosine 4x dx. Now I'm ready to integrate. I have a quarter on the outside. 3 halves becomes 3 halves x minus, minus sine, not cosine, minus sine 2x plus 1/8 sine 4x. That's a constant. I have to remember that this piece here came from this fact. I had a half out front. Let's change the color of pens. I already had a half out front. I have the cosine becomes sine of 4x, and I need to multiply it by the reciprocal of what's inside of there. That's where the 1/8 comes from. I am almost done. I can distribute. I get 3/8 x minus a quarter sine 2x plus 1/32 sine of 4x plus the constant. And that is it. So here's just a reminder of some stuff with cosine squared so I can divide things through. All right. Now, because, oh, sorry. This here, if I do this, I get 1 plus sine squared over cosine is tangent squared. X is equal to 1 over cosine squared is secant squared x. If I don't remember that, this gives me cotangent squared x plus 1 is equal to cosecant squared x. That's what this is trying to remind me of, my Pythagorean identities. So I have a tangent cubed x times secant squared x. I need to be careful and pay attention to what I have. I need to remember some of my derivatives. If I let u equal tangent x, then the derivative of u, or the derivative of tangent x, is secant squared x dx. So look at this. I have my substitution, u cubed du. So when I integrate, I get u to the 4th over 4 plus a constant, u being tangent 4th x over 4 plus a constant. So again, like in the previous sections, I'm trying to figure out how to manipulate these to get things I can make an easy u substitution. I will tell you some problems people will work out and do a harder way. You need to practice these. They will show up on your test and they'll be time consuming if you haven't practiced them. So again, if I let u equal tangent x, here's my du. So just like we did earlier with the sine problem, I end up 2 plus 3u plus u squared du. Integrate that, 2u plus 3 halves u squared plus u cubed over 3 plus a constant, replacing u with tangent again, 2 tangent x plus 3 halves tangent squared x plus 1/3 tangent cubed x plus a constant. Alrighty. We are about halfway through. There's a lot in this section. So in this problem, I see that I have the secant x tan x, but I also see I have a secant here, and this is a secant. So I'm going to say, well, let u equal secant x. Then du has to equal secant x tan x. That's a nice substitution, because then I have 2u cubed minus u plus 1 du. Again, I can easily integrate that. I get u to the fourth times a half minus 1/2 u squared plus u. And I want to add a constant. My u is secant, so I'm going to put that back in. Secant to the fourth x minus 1/2 secant squared x plus secant x plus a constant. So just to give us some ideas of what we're doing. In a problem like this, we said, like with the sines and cosines, we get everything in terms of secant, and I have a secant x tan x dx. So my u will be secant x, and my du would be secant x tan x. Or I get everything in terms of a tangent x, and I have a secant squared x, and I can let u equal tangent x, and du would be equal to secant squared x. And just to remind us of the Pythagorean identity, tangent squared x plus 1 is equal to secant squared x. So in here, what should I do? I have a tangent to the 6th secant to the 4th. Well, if I can end up with a secant squared, right, and everything else is tangents, I'm in good shape. And I can do that because I can rewrite this. I can say tangent to the 6th x secant squared x secant squared x dx. So I broke up this part here into two secants. Because again, we know that tangent squared x plus 1 is equal to secant squared x. So I can substitute. I say tangent to the 6th x times tangent squared x plus 1 secant squared x dx. And I can then say let u equal tangent x. So du has to equal secant squared x dx. By u substitution, I get a u to the 6th, u squared plus 1 du. Distribute my u to the 6th, I get u to the 8th plus u to the 6th du. I will integrate that, u to the 9th over 9 plus u to the 7th over 7 plus a constant. U, again, was tangent x. So tangent to the 9th of x over 9 plus tangent to the 7th of x over 7 plus my constant. All right, let's look at this one. Actually, we're going to skip this one. That wasn't supposed to be in here. Tangent x. All right, hold on for a second. All right, so this is what we know. We have tangent x is equal to the natural log. Whoops, did we skip a problem? Oops, sorry, we did skip a problem. Tangent x dx. We need to solve this. This is actually not a bad problem. We could rewrite this. You do not have to, what I'm showing you now is something that's kind of interesting, and we're going to derive something here. So we have sine of x over cosine of x dx. I can let u equal cosine of x, so du equals minus sine x dx, or minus du equals sine x dx. So now I can do a u substitution is all I'm trying to get at. So I end up with 1 over u du. When I take that, don't forget my minus on the outside, I take the natural, that becomes the natural log of the absolute value of u plus a constant. Put back, whoops, sorry, that's not supposed to be showing. Then I have my substitution, that's a minus the natural log of cosine x plus a c. Right, I can leave it that way, or it's a log, I could put the negative 1 inside. Natural log, if I put the negative 1 inside, it's cosine of the negative 1, or 1 over cosine x plus a constant, which is the natural log of the secant of x plus c. So what we've done is derived how do I take the integration of tangent x. That's all we've done. That's what's on the next page. So now we know that the natural law, if I take the integration of tangent x dx, then I'm just saying I know it's equal to the natural log of secant x plus c, or I could just say it's the opposite of the natural log of cosine x. And then I could say secant x dx. We didn't derive that one, but it's going to be given to you on the test, is equal to the natural log of secant x plus tangent x, the absolute value of that, plus c. The integration of cotangent of x dx, again, will be provided to you on the test. Natural log of the absolute value of sine x plus c, and then the integration of cosecant x dx is equal to the natural log of the absolute value of cosecant x minus cotangent x plus c. All of these will be provided to you on that sheet, including all this information on here, which is what we've been using. Secant squared x is equal to tangent x plus c. All this is stuff that you're supposed to know. So actually double check that sheet. I'm pretty sure this is on the sheet. So I'm going to check real quick. Okay, I just double checked. This is not going to be provided to you on the test. These are things that we're supposed to know. And the Pythagorean identities, we should know that secant squared x plus, I thought I saw that on one of these slides over here. But you can look at the sheet. I will have it posted so that you can see exactly what's going to be provided for you on the test. All right. So let's get started. I had the tangent squared of x. We want to work that out. Well, I'm going to rewrite this because I know how to take the integration of tangent x, but not necessarily tangent squared x. So let's rewrite this as the secant squared x minus 1 dx. Well, that's pretty easy because I know that the derivative of tangent is secant squared, so this becomes a tangent as I integrate tangent x minus x, and I don't want to forget my plus c. If I didn't remember that, I could have started off with saying it's sine squared x over cosine squared x dx. Then I could have done a substitution of 1 minus cosine squared x over cosine squared x dx. I could have break that up to be 1 over cosine squared x minus cosine squared x over cosine squared x dx. That gives me secant squared x minus 1 dx, which is where I started off over here. Boy, it's a lot easier if I understand my Pythagorean identities than as opposed to changing everything in terms of sines and cosines. It could definitely save me some time. So keeping that in mind, I have a cotangent squared x dx. I don't want to go breaking that all into sines and cosines again. That just seems way too much of a waste of time. But I do know that cotangent squared x is equal to cosecant squared x minus 1 dx, right? Because cotangent squared x plus 1 is equal to cosecant squared x. And we're supposed to know these Pythagorean identities. I can then easily integrate that. I know the integration of cotangent x is minus cosecant squared x. So I need a minus cotangent x minus x plus a c. And that's going to be my answer there. So now we can look at all this. This is everything we should know how to integrate now. So I'll give you a second to look at this and see what you know how to integrate. And this, again, is things I'm supposed to already know. Oops. These are things I should already know. Sorry. Having a little technical difficulties here. These are things I'm supposed to already know. So we have two more problems left to do. So we're going to look at this problem. And it's a integration by parts problem. I have a secant cubed x dx. So I'm going to say, well, let u equal secant x and dv equals secant squared x. So if u is equal to secant x, then du has to equal secant x dx. Whoops, secant x. I'm getting tired, I guess. Tangent x dx, and dv means v has to equal tangent x. So we're going to do our substitution. I get tan x secant x, right, u times v, minus the integration of v du, tan x times tan x secant x dx. And just to remind us, it's uv minus the integration of v du. All right, that's what we're doing. So now I have this part here, which I have tan x secant x minus the integration of tangent squared x secant x dx. Well, I don't know how to handle that tangent squared x. I can't just siphon off a tangent, right? Because I need either a tangent secant, which meant I had to have a secant, right? Everything in terms of secant, then I'd have a tangent secant, or I have to have everything in terms of tangent, and then I have a secant squared. So I'm going to manipulate the right-hand side. I'm going to rewrite tangent squared x as a secant squared x minus 1 times secant x dx. And I'm going to distribute. And I know I still have to address the left-hand side. Secant cubed x minus secant x dx. I'm going to bring this part down. Tangent x, secant x. Now that I have that, I can break this up into two different integrations. Secant cubed x. Distributing that negative also to here gives me a plus the integration of secant x dx. Well, I then have my original problem, going all the way back here, was a secant cubed x dx. So we're using the trick that we learned before. Secant cubed x dx is equal to tangent x secant x. And then this part here I can integrate, plus, and this is going to be on your sheet, remember, secant x plus tan x minus secant x, the integration of secant x dx cubed. So just so we can highlight and see where things are, this part is this part. I took this and integrated that part. And then this was already here. And then this part here came from the original problem. Whoop, and I forgot one part, my integration symbol. So bringing that minus secant cubed x to the other side, I get 2 secant cubed x dx is equal to the tangent of x secant x plus the natural log of secant x plus tangent of x, the absolute value, plus a constant. I'm almost done. I don't want that 2 on the other side. So we say that the integration of secant cubed x dx is equal to, multiply everything through by half, 1/2 tangent x secant x plus 1/2 the natural log of the absolute value of secant x plus tangent x plus a constant. So as we scroll through, we can go here and see that that's the exact same answer. I wrote tangent x secant x, I wrote secant x tangent x, same thing. One last problem. I have a problem like this. Sine of 3x cosine 5x dx. I don't know how to integrate this, but this is one of these that I would have a formula for you. This is a problem I told you, be careful. You'll have this on your sheet, so I expect you to get it right. So this says I have 1/2, it's similar to the form of 1/2 sine a minus b plus 1/2 sine a plus b, right? And if I have that, a is equal to 3x, b is equal to 5x. So by substitution, I have 1/2. A minus b is sine of minus 2x plus 1/2 sine a plus b, 8x dx. I can factor out that 1/2 from everything, making my life a little easier. And since it's an addition problem, I could break them apart or not break them apart and just do the integration. So now I need a 1/2 times, I need a minus 1/2 to, right? Because of this part here. I need a minus for the cosine, because the integration of cosine would give me a minus sign, but I have a plus sign, minus 2x, right? Plus, I need a 1/8 for that cosine there, minus cosine 8 over x, 8x, sorry, plus a constant. These are double negatives, so it's positive. So I have 1/2 times 1/2 cosine. Cosine of minus a is equal to cosine of a. So I'm just going to write this as 2x plus, whoops, not plus, minus 1/8 cosine 8x plus a constant. I'm going to distribute 1/4 cosine 2x minus 1/16 cosine 8x plus a constant. And that's what it should say under here. All right, that is everything for this section. Well, I'm sorry, there's one more slide just showing you. These will be provided to you again on the test, these rules. And this is just a reminder of what I just did using that minus, that rule. All right. All this will be provided for you on the test on that one sheet. You will be able to look at that online. Thank you very much. Hopefully you don't have too many questions. This is a pretty easy section. This was section 7.2. We're going to have one more section of this test, which will be section 7.3. All right, have a good day, and I'll see you in the next class.